X2, scores key, posted later this afternoon. Point value per Q 16 for X2, which means 384 total is earnable with a 250 base. Wait till we get to exam 3. Big time point value then. These are already big time, but that'll be bigger time. And what I'm going to do is to issue SQ2, SQ3 simultaneously. That way you can have these in your possession to work on. You're already in position to deal with SQ2 because that is based on stuff we've already done. As you will recognize when you see it. If I get the SQ3 part of this done, I'll release it today. Now, along with this, I will attach an evaluation form. You will see that the due date for this is targeted as next week, Thursday. And along with your submission of SQ2, SQ3, I will expect that you also submit an eval form in behalf of your discussion TA. The details of information requested for such are on the eval form. And if you want to stay ahead of the gate, EChem tomorrow, so get at it. Today, tonight, early hours of the morning, whatever have you. Now, let's get into the real nitty-gritty, so to speak, of chapter 21, which will show us how, I think, to better understand the fundamental thermodynamic components of a reaction system, delta H, delta S, which put together gives us delta G, by delta G equals delta H minus T delta S, and the same under standard state conditions, where each of these thermoterms has got the superscript 0 to identify standard state conditions. How do these conditions relate to equilibrium? And then back to our definition of delta G0 in terms of K for the reaction, the equilibrium constant. With that, to make this stuff come to light, we will analyze a couple of reaction systems. The first of which we now discuss. We talked about this back in chapter 17. A flask which is containing brown NO2 gas. Does the flask also contain N2O4 gas? We talked about this chapter 17. Remember that this reaction as written is exo or endo? That reaction is written. Exo or endo? Why? It's strictly bond breaking. Yeah. Now, do I encourage a bond breaking reaction to proceed by adding or subtracting heat, by warming or cooling the system? Warming. Yeah, I want to break bonds, I want to heat up the system. So if I wrap my warm paws around this flask, since the brown stuff is NO2, you'll see an intensification of color. Now I've got a flask inside this thermal bucket, which contains the very same system contents. Take a look at the color. Uh-oh. Now I got to get in there where it's cold. See any difference in color? This is far less intense, isn't it? Because in this far less intensely colored system, which of these from this system, if I turn this system into this system into this system, what reaction is occurring? That going that way? Going the other way, because that's bond forming and I'm cooling. on bond forming. So, by cooling, I favor bond forming, which corresponds to this thing being exo in this direction, where the heat that was lost by this system to become this system went into melting some ice. Now, my wife regularly wonders how I get my clothes so dirty. Don't tell her. With that, just to try to be sure you understand what's going on here, consider the following experiments. In this piston cylinder gadget, at 25 centigrade, 1 atmosphere external pressure, pretty much the conditions that are with us in this room, these are defined as normal lab conditions. Let us imagine that in this piston cylinder gadget we can place, at these conditions, 1 mole of N2O4 gas pure, which is colorless. And in a second piston cylinder gadget, let's imagine that at the same conditions I can place 2 moles of NO2 gas, the brown colored stuff. We'll now allow each piston cylinder gadget to stand for a good long time and answer the question, after standing for a good long time, we're going to pry open each piston cylinder gadget. What will we see? What will be the nature of the contents of each piston cylinder gadget after each has been allowed to stand a good long time? Now, for this system, which is bond breaking, the delta H zero part is larger than the T delta S zero part because delta S zero favors this. This change corresponds to an increase in system entropy. That's why delta G zero is plus. So if I turn this around, delta G zero at these conditions is minus 4.7 kilojoules, which we've just discussed. So I go back to this. What am I going to see in each pot after standing for a good long time? What will I find if I investigate the contents of each pot? Will I find out that in each pot I just have N2O4? Will I find out in each pot I'll have NO2? Will I find out that in this pot the NO2 gas has remained and in this pot the N2O4 gas has remained? Will I find any of these results? You recognize from the information we've so far considered that at these conditions, which is thermodynamically more stable stuff? Which is the thermodynamically more stable stuff? A mole of this or 2 moles of that at these conditions? 1 mole of N2O4 or 2 moles of NO2 gas? Which is the more thermodynamically stable stuff? Which one? N2O4 gas. I agree, that's correct. So will I find that the contents of this system remain unchanged and this converts entirely to N2O4? What will I find? Have you seen this statement? What will I find? Gas is a dynamic state of material, so reaction is certainly possible to occur in the system. What will I find? For long standing, forget kinetics. For long standing, I'm going to open up each piston cylinder gadget. Remember what we looked at over here? Now notice, while we were talking, I had both of these laid on top of the ice, and now their contents are rather similar, wouldn't you say? Practically speaking, identical. So do you think while we discussed this a reaction occurred? Because the system contained in the flask that was initially at room temperature, the more brown system became less intensely brown, didn't it? But in each vessel, now that there are same conditions, if I analyze the contents of each vessel, what will I find? Will I find that the NO2 N2O4 ratio in this vessel is the same as the NO2 N2O4 ratio in this vessel? Will I find that? Yeah, I'll find that. Because what I am showing you is at the temperature at which these flasks are presently existing, what condition exists? Equilibrium. Because equilibrium is the most stable thermodynamic state in which a reaction system can exist. So what am I going to find out after I open these things after they stood for a good long time? Well, first what I will see is that on standing, the volume, internal volume of this piston cylinder increases, and the internal volume of this piston cylinder decreases until the internal volumes are identical. And inside each, I will have at the same temperature and pressure condition. Or if you want to write it in the opposite direction, that's fine. Because that system is more stable than pure this, or any mixture of this with this, other than the equilibrium mixture. Let's take a look at this graphically. Here's a G-state graph. Now what's interesting about a G-state graph is that it is hypothetical. Because we cannot measure the absolute free energy for a sample of material. We can measure its absolute entropy, but there's no way to measure absolute enthalpy, which makes it impossible to measure absolute free energy, but we can still talk about it. Which form of a system is thermodynamically more stable? The system at a state of high G state, or the same system at a state of low G state? Which form of the system is more stable? The low G state. The lower energy any system has, the more stable it is. So what do you think about 2-year-olds? You want to spend your day traveling after a 2-year-old? Crawling, walking, getting into everything. You're going to get exhausted. That's a very high energy system. Now, I don't think we need to refer to the system, to our system as it exists when we are very low energy. No more motion. So for this system, we recognize that a mole of this at 25 centigrade 1 atmosphere is more thermodynamically stable than 2 moles of this. And the difference is, so if I arbitrarily and capriciously say this line corresponds to the G state of 1 mole of N2O4, then I can arbitrarily and capriciously say that the G state for the 2 moles of NO2 is up here higher. And the difference in these G state levels is 4.7 kilojoules depending upon the direction in which you travel, plus or minus. If I go from 2 moles of this to 1 mole of this at 25 centigrade 1 atmosphere, I'm looking at that reaction but going that way. That'll liberate 4.7 kilojoules. But if I'm looking at a mole of this converting to 2 moles of this, then the delta G0 is plus 4.7 kilojoules. Because you would have to put in that much energy if you wanted 1 mole of this to decompose entirely into 2 moles of this. But we recognize, doesn't matter which of these piston cylinders we start with, we're going to wind up with the equilibrium state. So tell me, how does G for the equilibrium state for this system compare to this G state? How does G for the equilibrium state for this system compare to this G state? Lower! Absolutely, because the G state for the equilibrium form of the system is the lowest possible G state that system can exhibit. Because it now, when it's at equilibrium, has no tendency whatsoever thermodynamically to change into something else. Now, if I start with 1 mole of NO2, N2O4 pure, and I label my graph as I go left to right as percent N2O4 dissociated, because as I go from N2O4 to NO2, N2O4 has to dissociate. N2O4 molecules have to break apart into NO2 molecules. Well, let's arbitrarily say, because what I meant to say is, in addition to that, at about 20% N2O4 dissociated, if I start with a mole of N2O4 at these NLC conditions, I'll be at equilibrium. So, well, let's write it this way. There's EQ. Now the chalk's at EQ. So the graph is showing us, if I start with a mole of this, I get a favorable change in free energy. Reaction is spontaneous. The sign on delta G is minus. Until I go here to the equilibrium mixture, which corresponds to about 20% of the initially 1 mole pure N2O4 having dissociated. On the other hand, if I start with 2 moles of NO2, I don't go over here. That's a favorable change in free energy. But I go over here because this is a bigger favorable change in free energy, isn't it? So if I ask you the question for this system, how does delta GR compare to delta G0R for this reaction? What's your answer? Let's go this way. Because if I go this way, well, since we put it as plus 4.7 kilojoules up there, let's start here. Okay? If I go from a mole of this to 2 moles of this, I got input plus 4.7 kilojoules. But that isn't going to happen, is it? Naturally. It's going to go here. And that is a delta G, which is minus, right? I went to a higher G state to a lower G state. That's a spontaneous change. So, here to here, plus 4.7 kilojoules. Here to here, whatever the change is minus. So it's certainly a more favorable change in free energy than the plus 4.7 kilojoules. If I start here, and I go here, I would gain 4.7 kilojoules, minus 4.7 kilojoules. But that isn't what happens. I go from here down to here. That's a bigger G state, change in G state. A more favorable change in G state. Because again, there's our true statement. So whatever system you start with, the NO2, N2O4 system, over here, over here, over here, over here, over here, I don't care where you're at. If it's anything but the EQ, a reaction will happen naturally as dictated by thermodynamics for that system to react until I got the equilibrium system. Now, let's proceed to get some more practical understanding of what's going on here. Thermodynamic properties of a reaction system. For starters, we have to recognize in addition to what we've said so far, we know how the standard state is defined. Pure liquids in the standard state, pure solids in the standard state, gases in the standard state if they're initially present at a partial pressure 1 atmosphere. Solute species are in the standard state at a molarity of 1. And there ain't no such a thing as a thermodynamic standard temperature. Now, most thermodynamic data is cited at 25 centigrade, since that's taken as normal lab conditions. But I can do standard state studies at any temperature, so long as the material components of the system exist at the temperature at which I wish to make the investigation. But if I want to do thermodynamic studies on an aqueous solution reaction, now I got a problem. You see, what we said a moment ago is that it is possible to determine the absolute entropies for pure substances. And for a perfect crystal at 0 degrees Kelvin, the absolute entropy of the substance, if it forms this perfect crystal, is 0. You set it in the notes, okay? But can I take a solution to absolute 0? Can I take a solution to any condition which approaches absolute 0 and have the solution still exist? If I take soda pop and put it in my refrigerator freezer and freezing occurs, will I have a solution? You like popsicles? I like popsicles. I used to eat a lot of popsicles when I was a kid. I like the blue ones. I think they were supposed to be raspberry flavored or something. I don't know, but I like those. Okay. So you're looking at this popsicle on a stick, which is practically speaking frozen soda pop wrapped around a stick. Is that a solution or is it a suspension? What is it? It's a suspension. Because when I freeze a solution, the solution is destroyed. The liquid solvent separates from the solute particles. They may all be in the solid state, but they're no longer homogeneously mixed. It's no longer a solution. So if I wish to do thermodynamic studies on a reaction in aqueous solution, and we're doing these kind of reactions, practically speaking, more often than any other kind of reaction, or we're interested in these kind of reactions more often than any other kind of reactions. You think reactions which take place in our system are reactions which are taking place in aqueous solution? Or do you have benzene running through your veins? Gasoline? Oil? Pure alcohol? I don't think so. You got water as your solvent system. Blood, sweat, tears, and on we go. So since a solution cannot be taken to low temperatures, let alone absolute 0, without destruction, if I want to do thermodynamic studies on a solution, I have to define a reference point. And here's the reference point. For the formation of H plus aqueous at standard state conditions, what's the molarity of H plus aqueous at standard state conditions? What's the molarity? What is it? What is it? The molarity at standard state conditions. What did we say defines a solute to be present in the standard state? 1 molar. So the H plus aqueous concentration is 1 molar. What's the pH? 0.00 and forever. An absolute pH of 0.0 blah 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 blah, as best as we can establish by making measurements in the laboratory. For forming this pH 0.00 solution, delta G sub F super 0 is equal to delta H sub F super 0 is equal to delta S sub F super 0 and set equal to 0 arbitrarily and capriciously. Because you can't measure this as an absolute value. So we're defining it. This is our thermodynamic standard state reference point for solution studies. And from this I can get these thermodynamic properties for all other solution species. There's illustrations of this at the end of chapter 20 for those of you who are interested. It's not difficult. It's just simple application of Hess's law based on this defined condition. Now what is this also? I mean, here's the reaction. This corresponds to forming H plus aqueous. Half a mole of hydrogen gas reacting in the presence of water liquid to become H plus aqueous with electron loss. And it's defined at 25 centigrade because of the delta G0 in there. Okay? Just a defined condition, no more, no less. We take the change in free energy for this, the change in entropy for this, the change in enthalpy for this, all 0. Is this a reaction which I can run by itself? Is this a reaction which I can run all by itself? Because if I could run it all by itself, I could measure the change in free energy and all the other properties. Is that a reaction which I can run by itself? I already told you this story. Because if I could run that reaction by itself, then H plus aqueous by itself would be stable, and this electron product would be stable. And then Horvath can open up his electron store, because I'll collect the electrons, put them in a bottle. You know, electrons, they don't take up much volume. And if I give you a 1 pint size of electrons, I suspect you'd have enough electrons to power your electricity requirements for the next 2 bazillion years. You know, you go home, pour them in the socket, call up GRU, say, hell with you, I don't need you anymore. But you can't do that, because this is said to be a half reaction. It's only half a reaction. You cannot run a reaction in which you start with neutral stuff and make only positive substances as products. This is really not considered a substance, because practically speaking it's weightless, massless. So this also means that since H plus aqueous is at least this, it follows that H plus added to water liquid to make the hydronium ion, the change in free energy, the change in enthalpy, the change in entropy for this reaction is also 0. Now then, if I've said, let's put the aqueous on here. If I said that all the thermodynamic properties, formation for this stuff are 0, okay? And the change in free energy, blah, blah, for this whole reaction is 0. How does delta G sub F super 0 for water liquid compare to delta G sub F super 0 for hydronium ion aqueous? How do these two thermodynamic properties compare for those two species at 25 centigrade? For H plus aqueous, 0 by definition. And as it follows from this, delta G 0, etc. for that reaction is 0. So how must delta G sub F super 0 for water liquid compared to delta G sub F super 0 for hydronium ion AQ? They got to be equal, but they're not 0. It's each minus 237.1 kilojoules. Just another data point that I've considered so many times I know it. You can look it up in the table at the end of chapter 20. Table 1, thermodynamic properties. Now then, we've said all we need to have said to start to do practical thermodynamic analysis of a reaction system, which I think is the best way to get you to see how useful these fundamental thermodynamic properties of a reaction system are. With that, we're going to give you this as a definition. It's not really a definition. It can be derived from fundamental thermodynamic relationships. But it involves and rests on entropy considerations for gases and heat capacities and a lot of stuff that I don't wish to bother with. If you go to an upper level course in physical chemistry, you'll be bothered with that stuff. Now, I'm not going to bother you with that stuff now. Perhaps you've already noticed that relationship is on your information sheet, so that if you need to use it, it is there. You don't have to memorize it. But it does show you how the change in free energy for a reaction is equal to the standard change in free energy for the same reaction, to which we add 2.3 R, the ideal gas constant expressed in energy, common energy units, joules, kilojoules, times T in Kelvin, times log Q. We already know what Q is. Back to chapter 17, again considered in chapter 19. Q is an expression for a reaction system which is exactly identical to the equilibrium constant, except that Q considers any imaginable set of conditions, whereas the equilibrium constant considers exclusively equilibrium conditions. But if delta GR is 0, the system is at equilibrium, right? No more change in free energy. We considered that the other day. So at equilibrium, delta G0 sub r is minus 2.3 RT log K, the equilibrium constant, because when this equality exists, the change in free energy for the reaction is 0, and Q is equal to K. This is quite useful. Do you recall why we said this is quite useful? Because it's practically speaking not possible for any reaction system to go to the lab and directly measure delta G 0. But what is the easiest thermodynamic property for a reaction system to measure? Do you think it might correspond to when the system is in its most stable state? When is the system in its most stable state? When it's at equilibrium, because then it's not changing anymore. It sits there. Time means nothing. Kinetics means nothing. You can make a measurement, go across the street for Burger King, whatever you want, come back next Tuesday, have some pizza and beer, whatever. The system is still there at equilibrium. Nice and stable, hasn't changed. So if you can measure K, the equilibrium constant for the system, which is arguably the easiest property to measure for a reaction system, then you can get delta G 0 for the reaction system. That's why this thing is useful. Now then, top of page 2112. Question 2123. Asks about water, physical changes, for which delta G 0 as well as delta G is 0. That means we're looking at a reaction system or a system which is at equilibrium with each system component present under what conditions? Under what conditions? Under equilibrium. Well, we said equilibrium exists. Equilibrium exists for a system, and for that same system, delta G 0 is 0. So what conditions am I at? What's the superscript 0 say? Standard state conditions. So regarding water, since I think it's the simplest and most obvious case, can I create this system at standard state conditions? Because notice with the double arrows, that means equilibrium. Can I create this system at standard state conditions? What are the conditions I must create? I'm listening. What external conditions must I create? What environment must I have this system at if for this system this is true? At equilibrium. Right? What must be the conditions? What are the conditions? Pure liquids, pure solids, by definition, are in the standard state, provided the pressure acting upon them is 1 atmosphere. Okay? And if the pressure acting on this system is 1 atmosphere and this equilibrium condition exists, what temperature am I at? 0 centigrade. How about that? I want this to be at equilibrium in the standard state, this system. What conditions must I establish? I hear 1 ATM. I don't know what that means. Partial pressure of what is 1 ATM? Water vapor. It's got to be at a partial pressure of 1 ATM. Right? Isn't that the way we define standard state for gases? So, if P H2O gas equals 1 ATM, what must be vapor pressure for water liquid for this equilibrium to exist? 1 ATM. The tendency for this to evaporate, its vapor pressure, has got to equal the tendency for this to condense, its partial pressure. And at what temperature does this exist? Minus 2,000 centigrade? Minus 8 million Kelvin? At what temperature does this exist? What is it? What? These conditions. Because at 100 centigrade, the vapor pressure for water liquid is 1 atmosphere. And so if this is present in the standard state, its partial pressure is 1 atmosphere. So this equilibrium exists, because the vapor pressure for this stuff will equal the partial pressure for this stuff. And on we go. I mean, this equilibrium can exist at a bunch of different temperatures. But if it's at equilibrium in the standard state, it's only for these specific conditions. Now let's be even more practical with the intention of going forward with showing you how this stuff can be put to use in regard to understanding a reaction system. For starters, back to teacher's favorite weapon. But now, rather than dissolving this stuff, we're going to consider the tendency of this stuff to decompose into the indicated products: calcium oxide solid and CO2 gas. Let's first consider this at 25 centigrade. 1 atmosphere external pressure. Practically speaking, the conditions that are with us here in this room. See any gas coming off this? It's calcium carbonate mainly. No gas coming off. What's the equilibrium constant for this thing? Well, first we'll remind you about its thermodynamic K. The thermodynamic K, because of the way it's defined, is a ratio of activities. Now we're going to not deal with activities. We're going to stick with partial pressures and concentrations. But since a thermodynamic K has no units, because it's a ratio of activities, the terms contained in thermodynamic K are ratios, so no units. We're not concerned with dealing with that arithmetically. What's the equilibrium constant for this reaction? I want you to write the equilibrium constant for this system right now on your paper. So we're now looking at this system this way. What's K for this system? Put on your paper, the equilibrium constant. Remember the kinds of what components an equilibrium constant has, chemically speaking? There are only 2 components. What are the 2 components in general? Solutes, not reactants, products. I want to know what reactants, what products. Solutes and gases. That's it. There's only one gas in this thing, and the others are solids. So here's the thermodynamic K. A unitless partial pressure for CO2. It's not really, this is going to be activity. I mean, it won't even have activity units. Got no units. But to deal with these unitless equilibrium constants is, practically speaking, of very little value, at least to us at this stage of the game. So, if I want units for a reaction, and I've calculated the equilibrium constant for the reaction from fundamental thermodynamic data, like with delta G zero data, I calculate the K. I'm not going to get any units. How will I get units if I need them to do equilibrium analysis? If I don't have units for an equilibrium reaction system, because I calculated the equilibrium constant from thermodynamic properties for the system, like changes in standard free energy, which will give me no units. We'll show you this in a moment. But to analyze the system, I need to apply or attend units. Where do I get these units? Make them up? I look at the reaction itself. Because I know if I wrote this reaction and its equilibrium constant, which we have, knowing that the equilibrium constant would be expressed as the partial pressure of CO2 gas, what unit would I apply to this? What? What units do I apply to pressures? What unit have we chosen to apply to pressures? Goody. P CO2 in atmospheres. Okay? Now then. From table 1. That's this thermodynamic properties data table at the end of chapter 20, which we have looked at previously, like thermodynamic properties, pardon me, for carbon graphite, carbon diamond, stuff like that. We can, for this reaction, at 25 degrees centigrade, because the data in that table are cited at 25 degrees centigrade. Measurements made at 25 degrees centigrade. There's delta H0R. Does that favor this thing going under standard state conditions, or stand in the way of this going under standard state conditions? Is delta H0 for this reaction or against this reaction? For or against? For or against? What's this mean? Does this mean exo or endo? Means endo, doesn't it? And if I want an endo reaction to go, I got to put energy into it. Does that sound like it's going to happen all by itself? No. So is this for or against? Against. Now then, you shouldn't be surprised that this is a positive change in standard enthalpy, because this is 1 mole of material coming apart to becoming another mole of solid material, but a mole of gas material. Hey, when you start converting solids to gases, you get a big favorable change in entropy. I mean, pardon me, when you take this apart and turning it into 2 moles, that's going to cost you, in the main, energy to break bonds. Pardon me, I got tangled up with the change in entropy, with the change in enthalpy. But for this reaction, you think the change in entropy is favorable? You think if entropy ruled the roost, this thing would go? You betcha. Because, again, this is where I tangled up my tongue just a second ago. This is taking 1 mole of stuff and envisioning the possibility of converting 1 mole of this stuff to another mole of solid plus a mole of gas. So a big favorable change in entropy. The value is plus 162.7 joules per K. So, at standard state conditions, which thermodynamic property is controlling this system? Is it this, which is against the reaction, or this, which is for the reaction? You see this falling apart in the CO2 and calcium oxide right before your eyes? Calcium oxide, because of the oxide ion component, strongly basic, would burn my fingers. No gas liberation. So for this system, at these conditions, delta H0 controls the outcome. Now then, to get further at the thermodynamic analysis of this system, we want to get the change in free energy and the corresponding value for the equilibrium constant to see what the equilibrium constant tells us. From our delta G0 equals minus 2.3 RTK, we're going to rearrange that to get log K. And I'll put that in here. Up, up, up. Left out a step, pardon me. From delta G0R is delta H0R minus T delta S0R at 298K. We put in these numbers, and the multiplier on change in entropy is 298K. We will get plus 129.0. So certainly non-spontaneous in the indicated direction under standard state conditions. Or if you wish to say spontaneous under standard state conditions in the reverse direction, that's true. If I assemble the system, or we were able to assemble the system at these conditions, some of this, because it's in the standard state, some of this, and this at a partial pressure of 1 atmosphere, woo, it'd go this way. The CO2 would be readily absorbed by calcium oxide and convert to this stuff. So, to calc K, it's all on a mole basis, so I'm not putting mole in there. We put in the required data. There's minus free energy. Whoop. Unit conversion 2.3. Whoop, 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 whoop. This doesn't belong there. Do the arithmetic. If you look at the units, since we're calculating this equilibrium constant from thermodynamic properties for the system, no units left. We just get a number. The log of the number is minus 22.64. So, okay, any log of that. .3 times 10 to minus 23. But I want units. Whoop. Where do I get the units? We said this a moment ago. Just look at our reaction system. Atmosphere, since the only component of the equilibrium constant is carbon dioxide expressed in terms of its partial pressure. Okay. Now then, just to be sure we got this unit stuff understood. What if I chose to analyze this very same system but with different coefficients? 0.5 moles for each system component. Now to get the value for K, what would I do to this number? We did this in 17, now we're doing it again. Take the square root of that number. What would be the units? ATM to the 1/2. Well, I feel like being hoggish. I want to look at this from a 3 mole, 3 mole, 3 mole standpoint. Now what do I do to get the K value? Cube it. And the units? Atmospheres cubed. That's all there is to that part. Now we proceed. What does this K mean? Well, to get a better idea what the K means, we'll ask a question. Questions in the notes. At 25 centigrade, since the data we've considered is at 25 centigrade. External pressure 1 atmosphere, so-called normal lab conditions. I'm going to get me a nice big flask. .0 liter volume. Nice big flask. Okay? And I'm going to get inside this flask with gadgetry, and I'm going to remove every CO2 molecule. It's got oxygen molecules, I don't care. Nitrogen molecules, I don't care. But no CO2 molecules, okay? 10.0 liters, initially free of CO2 gas, okay? And in here, I'm also going to place, there it is, calcium carbonate. See it? I put it in there. That's it, okay? Stopper the flask. So above this calcium carbonate, pure calcium carbonate in the flask, at these conditions, I have introduced pure calcium carbonate. System is closed. And inside the flask, at present, there are no CO2 molecules. What will happen? Under these conditions, will a reaction proceed? Because if it proceeds, then the reaction which we are considering is spontaneous. Because we haven't done anything but put some pure calcium carbonate in this big 10-liter flask, sealed it, and ensured that there are no CO2 molecules initially in the flask. Will a reaction proceed?
Yes, until it reaches 2.3 times 10 to the negative 20 degree pressure, steam to 9.
Yes! Our reaction proceeds spontaneously until this condition is achieved. Isn't this corresponding to equilibrium? And that's PCO2 gas. So when that calcium carbonate in that flask decomposes until I get a partial pressure of CO2 of 2.3 times 10 to minus 23 atmospheres, okay, until I get that, that system reacts spontaneously. Okay? So I put the calcium carbonate in there, the reaction occurred until this PCO2 was developed. So we'll now ask this question. How many CO2 molecules is this? 10-liter flask. Well, if I want to consider quantities of gases, what do you expect is the relationship that I will have to use for the calculation? PV is nRT. Okay? So I'm going to write this. There's my system volume. Now I want R with what units? Because I'm going to have pressure in atmospheres. And I'm going to have system in liter volume. So what kind of units do I want on R? Do I want joules per kmol? Because I got atmospheres in, pressure expressed in atmospheres and volume expressed in liters. Do I not want R expressed in units that will mesh with these units? Does 0.0821 sound like a number you remember? So now I'm going to write R as 0.0821 liter atmospheres per kmol, and I'm operating at 298 K. And what pressure do I write up here for pressure? 2.3 times 10 to the minus 23 atmospheres. All right? Now when I do this arithmetic, I get 9.4 times 10 to minus 24 moles of CO2. But I said, how many molecules? If I got moles and I want to go to molecules, what do I need to know? Avogadro, are you here today? You with us today, Avogadro? You remember your famous number? 6.02 times 10 to the 23rd particles, whatever they might be, per mole. And in this case, the particles are molecules of CO2. So what we're going to do is we'll do one additional piece of arithmetic. And I will get out my calculator, and to 2 sig figs I get 5.7. Will you accept that result? Is it physically possible to have 0.7 of a CO2 molecule? You know? Is it physically possible to have 0.7 of a CO2 molecule?
Instead of 0
5.7 molecules. That's what I got. Right? 5.7 molecules of CO2. I can get to 5 molecules of CO2, but can I get to 0.7 molecules of CO2? I mean, can I take 0.7 of a chair? Well, but then I got junk. I don't have a chair anymore. Can I take 0.7 of a people? Then I got a mess. I don't have a people anymore. So, the best I can do is to round this to the nearest whole number and call it 6 CO2 molecules. Wow. 1, 2, 3, 4, 5, 6. There they are. Does this serve to indicate why this stuff in this room right now does not fall apart whatsoever? You think per every 10-liter volume of this stuff we call air, there are more than 6 CO2 molecules? There's a hell of a lot more. I am thwarting this CaCO3 decomposition. Because as soon as I got a partial pressure of CO2 in this room, which is bigger than that, it's not going to fall apart, this calcium carbonate stuff, is it? Now then, statement. This calcium oxide product of this reaction, did I erase the reaction? That's terrible. This calcium oxide product of this reaction is an important commercial stuff. Last I looked, it's in the top 10 in tons produced per year of pure chemical substances by the American chemical industry. So we'll write valuable stuff. You think there's any of this valuable stuff made here in Florida? You think Florida, geologically speaking, has a lot of areas which are rich in calcium carbonate? Do you know why Florida tap water is commonly fairly basic? Again, last I checked, Gainesville tap around about 9.5 pH. Of course, the Florida aquifer rests over large, substantial mineralogical deposits rich in calcium carbonate. Phosphates as well, but carbonates. Hey. So if you want to make this valuable stuff, calcium oxide, you think you can make it from this stuff? You're damn right. Now tell me the conditions which have to be established to make calcium oxide from this stuff. Tell me what we have to do. You remember the fundamental standard state, thermodynamic standard state components of this system? Delta H zero, again but the delta S zero was for it, wasn't it? So what do we do to magnify the impact of a favorable change in entropy? What do we do? Add heat. Let's heat this thing up. So comes the next question. At what T is this system? At EQ in the standard state. At what T is this system? At EQ in the standard state. Now if it's at EQ in the standard state, what's delta G zero for this transformation? Zero! Ha-ha! I.e. when delta G zero R equals 0. And when delta G 0 R is equal to 0, how do delta H 0 R and T delta 0 R compare? Delta H 0 R and T delta S 0. Thus, this applies at these conditions. So you put in the delta H 0 value, you put in the delta S 0 value, make the appropriate unit conversion, because on that side you'll have joules and this side you'll have kilojoules, and calculate the corresponding Kelvin temperature. And when I do this arithmetic, I get a temperature of 1091 K. You can plug in the numbers. What is the significance of this 1091 K? It means in an atmosphere of CO2 at a partial pressure of 1 atmosphere, if I take calcium carbonate and heat it to a temperature above 1091 K, as this stuff decomposes, so long as the pressure of CO2 above the system, because now this thing is going to produce CO2 all over the place, as long as the pressure of CO2 above the system stays 1 atmosphere, the calcium carbonate is going to continue to decompose. So if I do this in the open atmosphere without closing the system, so the CO2 as I make it can run away, I'll make me a whole bunch of calcium oxide pure, just by continuing to heat this stuff in the open atmosphere at a temperature above 1091 K. And they do that extensively, right here in Florida, to make a bunch of calcium oxide. We'll pick it up from this point tomorrow. Tomorrow, finish 21 into 22.